Evaluate each to determine if the statement is true or false. So what we're going to do is find each part of this, and you'll notice the similarity between this one and one that was on your homework. So we'll just take and we'll deal with this first one and say log base 2 of 2 equals x. We'll do log base 2 of 16 equals y. Log base 2 of 32 equals z. And then we're going to have to do some other one for this one over here. We'll go log base 2 of 8 equals a. So over here we have 2 to the x equals 2. X equals 1. Log base 2 of 2 is 1. 2 to the y equals 16, and 16 is 2 to the 4th. So y is 4. 2 to the z equals 32, which is 2 to the 5th. So z equals 5. 2 to the a equals 2 cubed. So a is 3. Let's plug them in. We have 1 plus 4 equals 5. Yes, that's true. 3 minus 1 equals 2. Yes, that's true. 4 equals 4 times 1. Yes, that's true. And what that is just trying to show you with an example of what we're going to deal with in our rules here. In general, if x and y are positive real numbers and b is greater than 0 and b is not equal to 1, then what is our rule? Let's look at 1a. We had, notice a relationship here. We have the same base in these numbers, the same base, and then what's the relationship between 2 and 16 and 32? If you multiply 2 times 16, you get 32. So if you have something like 16 times 2, this can be broken up to log base b of x plus log base b of y. Now, why does that work? What you have to remember is, what is a log? A log is an exponent. And what are we dealing with here is multiplication. So let's review a second. What if we had x to the a times x to the b? What do we do with them? We would add the exponents, so it's x to the a plus b. Similarly, we have log base b of xy is log base b of x plus log base b of y. On the second one, that would be like our second example. What's the relationship between 8, 2, and 4? 8 divided by 2 is 4. So in other words, if we have log base b of x over y, it's log base b of x minus log base b of y. And that would be like our rule that says x to the a over x to the b equals x to the a minus b. If I have log base b of x to the k, what that means is log base b of x times x. How many x's are we multiplying there? We have k of them. So that's basically the same as this rule, applied multiple times. So we'll have log base b of x plus log base b of x plus log base b of x. How many of those are we going to have? We will have k of them, and so the rule is log base b of x to the k equals k times log base b of x. Or in other words, that exponent can come down as a multiplication. And that's what multiplication is. We think of it as repeated addition. And we've used this rule before, but this is just the formal rule. Log base b of x equals log base b of y. The base of the logs are the same, so therefore their arguments are the same. X equals y. Now we need to know those rules. You want to understand them, be able to recall them easily, and not have to spend a lot of time thinking about them. So let's take a look at this next piece. Here's some examples using these rules. On the first one, what we're going to do is just simplify. Now you have to be careful about these kind of things, especially with these negatives. And this first one's not as bad as the third one there. We can do this in stages. Log base b of 5 times 5 minus log base 7 of 3. I think I said log base b, so log base 7. And that's 25. And now when we're subtracting subtracting the logs, that means we're going to divide it within one log. So log base 7, again, the bases have to be the same here. So we have log base 7 of 25 over 3. Now remember to write the 7 at the bottom of the log. It's not at the same level. Over here, what does this 1/2 mean when it's in front? That's using our third rule above. So this can be written as log base 9 of 25 to the 1/2 power minus log base 9 of 4 squared. So we have the subtraction of two logs with the same base, so we can combine it to one log, and we're going to divide those. Now 25 to the 1/2, that's square root of 25, which is 5. And then we're going to divide that by 4 squared, which is 16. On the next one, we have log, or natural log, of m to the 1/2 power minus the natural log of n squared plus the natural log of p cubed. Now this is one we have to be careful. What does the subtraction apply to? It only applies to this natural log of n squared. It does not apply to anything else. So typically it's better to do this one in multiple stages. So we'll have m to the 1/2 divided by n squared. And then the better we get at it, we can start seeing that this will be ln of natural log of m to the 1/2 times p cubed divided by n squared. And that's all in that natural log. Here's another way to do these kind of problems in terms of demonstrating whether or not you understand how to deal with this. So I have a problem. Log base b of 2 is a. I don't know what b is, and I don't know what a is. Log base b of 3 is capital B. When I see a problem like this, I notice I have log base b. It has to be the same base there. And this is a typo there. That should be a b. So we have log base b of 72. What we need to do is write 72 in terms of 2 and 3. Basically, you need to deal with the factor tree there. So we can have 8 and 9. 9 is 3 times 3. 8 is 4 times 2, or in other words, it's 2 times 2 times 2 times 3 times 3. So we have log base b of 2 cubed times 3 squared. Now I want you to actually write those steps. Log base b of 2 cubed plus log base b of 3 squared. Now even here, you still need to go to that next step. What I want to do is clearly see log base b of 2 and log base b of 3, which is what we're looking for here. So we have 3 log base b of 2 plus 2 log base b of 3. Now we can see that this is 3 times a plus 2 times b. And on this next one, there's multiple ways you can go about dealing with it. We have log base b of 1/12. You could say log base b of 1 minus log base b of 12. Now we need to factor down 12, and 12 is 4 times 3, or 2 times 2 times 3. So this is minus log base b of 2 squared times 3. Now note that we have a minus here, and what's log base b of 1? Well, in other words, b to what power is 1? That would be 0. Now what we have to do is be very careful about this negative sign, because the negative sign applies to everything, this whole thing. Log base b of 2 squared plus log base b of 3. And I can distribute that, and I'll bring this 2 down at the same time. So it's 2 log base b of 2 minus log base b of 3, or in other words, negative 2a minus b. All right, let's go to the next page. we have to simplify this stuff. Now we see this 3 there, and you can see it on your papers. So it's 10 to the 3 log of 5. That 3 is a coefficient of the log. It can go to the exponent. So this is 10 to the log of 5 cubed. Now we could treat this a couple of different ways, but at this point we should realize what's the base of this exponential and what's the base of this log. The base of the log, remember, it's a common log. When it's not written, it's a base 10. Y equals 10 to the x and y equals log base 10 of x are inverse functions, and so this is just going to give us 5 cubed, or 125. That's a small enough number you can just multiply that out. Similarly, we have e to the ln of 5 cubed, so that's just going to give us 5 cubed as well, or 125. The last one's a little bit different because we have 1 plus this 2 log of x, but we can use the reverse order of our exponential rule that we reviewed on the previous part. X to the a times x to the b equals x to the a plus b. So that'd be 10 to the 1 times 10 to the 2 log of x. So 10 times 10 to the log of x squared. And again, this one part, 10 to the log of x squared, is just x squared. So this gives us 10x squared. Express y in terms of x. Again, for these kind of problems, there's going to be multiple ways to go about it. There's no one right way. I'm just going to do one. So first thing we're going to deal with is that coefficient. So we will rewrite it as log of x to the 1/2. Now we can combine these two into one log because they have the same base. So it'd be log of y times the square root of x equals the log of 3. Now notice here we have two logs that are equal with the same base, so therefore their arguments are equal. Y times the square root of x equals 3, or in other words, y equals 3 over the square root of x. And we could rationalize this and multiply by root x over root x to get 3 root x over x. On the next one, we have, this one's a little bit different. When I see this, we could treat this, again, multiple different ways. Take a look at what this says here, though. Notice that there is no log over here. There's no natural log at all. It's just 3 minus 0.05 to the x. This can be treated just like you would a number. And if you need to, you could do something like let a equal 3 minus 0.05x. So this would say ln of y equals a. Now this is a log equation. Can I transform it to an exponential equation? The base of the natural log is e. A log is an exponent, so my exponent's a equals y. So in other words, e to the 3 minus 0.05x equals y. Or in other words, we have e to the 3 times e to the negative 0.05x. And if this would be fine for what we're going to deal with. If you wanted to, this negative exponent could be, so it's moved down, so it's 1 over. This could be written as e cubed times 1 over e to the 0.05x. Let's take a look at the next one. It's very similar. Instead of doing this substitution like we did on b, let's do it without it. What is the base of this log? This is basically a log equation here. The base is 10. So 10, what the log equals is our exponent. 10 to the 2 plus 0.05x equals y. Or in other words, 10 squared times 10 to the 0.05x. Or in other words, 100. Now we could find an approximation for this, and I just want to point this out, that I could write it like this. And what is this basically saying? A times b to the x. This is an exponential equation. And let's take a look at this last one. Given the graph of log base b of x, so let's graph that thing. Remember, all of our log graphs look like this. It crosses at 1, and when we get out to b, that gives us 1 for the y value. What does this do to the graph? We could take a look. There's again a couple different ways. I did a problem similar to this earlier when we looked at number 3, part B, where we had log base b of 1 over 12. This time I'm going to do it a little different than that. Instead of saying log base b of 1 minus log base b of x, I'm going to call this 1 over x as x to the negative 1. So in other words, negative log base b of x. So what does that do to the graph? Well, that's saying negative f of x, if f of x is our log base b of x. So what does that negative f of x do to the graph? It's affecting the y values. So it says all the y values must change sign. What was positive now becomes negative, and what was negative now becomes positive. So that graph would be, let me put it in a different color here. Something along the lines of that. And this would be log base b of 1 over x. And that's it.